Today's documentary is about the unanswered questions. Question 1. Is time travel possible? Time travel has fascinated humans for centuries, but here's what most people don't know. According to our best understanding of physics, time travel isn't just possible, it's actually happening all the time. You're time traveling right now, just very slowly, into the future at a rate of 1 second per second. But can we go faster? Can we skip forward years or decades? Can we go backward? The answers are more complicated and more interesting than you might think. Einstein's theory of relativity tells us that time is not absolute. Time passes at different rates depending on how fast you're moving and how strong the gravity is around you. If you traveled in a spaceship at close to the speed of light, time would slow down for you relative to people on Earth. You might experience a year while decades pass on Earth. When you returned, you would have traveled into Earth's future. This isn't speculation. This is proven physics. Astronauts on the International Space Station age slightly slower than people on Earth because they're moving faster and experiencing slightly less gravity. The difference is tiny, just a few milliseconds over months, but it's real and measurable. Atomic clocks on GPS satellites have to be constantly adjusted for these relativistic effects, or your phone's map would be wrong by miles. So traveling to the future is not only possible, it's practical. If we built a ship that could travel at 99.99% the speed of light, you could travel thousands of years into Earth's future while experiencing only a few years yourself. The technology is beyond us right now, but there's no law of physics preventing it. But going backward in time, that's where things get truly strange. Einstein's equations actually allow for closed time-like curves, paths through space-time that loop back on themselves. In theory, you could follow one of these paths and return to a time before you left. These paths can exist near rotating black holes, in wormholes, or in exotic types of matter with negative energy. But here's the problem. If you traveled back in time, you could potentially create paradoxes. The most famous is the grandfather paradox. If you went back and prevented your grandparents from meeting, you would never be born. But if you were never born, you couldn't go back in time to prevent them from meeting. It's a logical contradiction. Some scientists think the universe prevents these paradoxes by making backward time travel impossible, even if the equations allow it. This is called the chronology protection conjecture. Whenever you try to create a time machine, something goes wrong. Quantum effects might create infinite energy at the point where the time loop closes, destroying the time machine before it can work. Others think paradoxes might be resolved by parallel universes. When you travel back in time, you don't actually change your own past. Instead, you create a new timeline, a parallel universe where you exist but were never born. Your original timeline remains unchanged. You can't change your past because your past and your future are now in different universes. There's another resolution called the Novikov self-consistency principle. Maybe the universe only allows time travel if it doesn't create paradoxes. Any action you take in the past was always part of history. You can't kill your grandfather because you didn't kill your grandfather. The timeline is self-consistent, like a loop with no beginning or end. But here's something that should make you uncomfortable. If backward time travel is possible, even in principle, where are all the time travelers? If humans or any other civilization ever developed time travel at any point in the future, they could travel to any point in the past. They could be here right now. But we don't see them. Why not? Maybe time travel is simply impossible, and there's something wrong with our physics that we haven't discovered yet. Maybe time travelers are here, but hidden. Maybe they have strict rules about not interfering with the past. Or maybe, and this is a dark thought, civilizations never last long enough to develop time travel. There's also the possibility that we can't travel back to a time before the time machine was created. In this view, a time machine is more like a door than a vehicle. You can only travel back to when the door was first opened. If no one has built a time machine yet, we can't receive visitors from the future. Recent discoveries in quantum mechanics have made the picture even stranger. Quantum entanglement seems to allow information to correlate across time as well as space. Some experiments suggest that measurements in the present can influence the past. This doesn't mean we can send messages backward in time, but it suggests that time at the quantum level is even weirder than we thought. The question of time travel matters because it's really a question about the nature of time itself. Is time a dimension like space that we can move through? Or is it something fundamentally different? Is the past still real, existing somewhere we might return to? Or does only the present moment exist, with the past gone forever? These aren't just philosophical questions. The answers have implications for how we understand causality, free will, and the structure of reality. And we still don't know what those answers are. Question 2. What is consciousness? Here's a question that might seem out of place in a discussion about space. What is consciousness? But this is actually one of the most profound questions in all of science, and it has everything to do with understanding the universe. You are conscious right now. You're experiencing these words. You have thoughts, feelings, sensations. There's something it's like to be you. This inner experience, this subjective feeling of awareness, is consciousness. And we have absolutely no idea how it works or why it exists. The puzzle is this. Your brain is made of atoms. Atoms are just particles following the laws of physics. Nowhere in the equations of physics is there anything about experience or awareness. You can completely describe a brain in terms of neurons firing, chemicals moving, electricity flowing, but none of that explains why there's an experience happening. Why aren't we just biological robots, processing information without any inner life? This is called the hard problem of consciousness, and it's different from the easy problems. The easy problems are things like explaining how the brain processes information, forms memories, or controls behavior. These are incredibly complex, but they're the kind of questions we know how to approach. The hard problem is explaining why all that processing feels like something. Some scientists think consciousness emerges from complexity. When you get enough neurons connected in the right way, consciousness simply appears, like how wetness emerges from water molecules. We can't find consciousness in individual neurons, but maybe it exists at a higher level of organization. Others think this is backwards. Maybe consciousness is fundamental, a basic feature of the universe like mass or charge. In this view, even particles might have tiny amounts of consciousness, and our rich inner lives emerge from combining countless tiny conscious moments. This idea is called panpsychism, and while it sounds crazy, some serious scientists take it seriously. There's a theory called integrated information theory that tries to measure consciousness mathematically. It says consciousness arises from how integrated information is in a system. The more integrated, the more conscious. By this measure, your brain is highly conscious. A computer running simple programs is not, and something like the internet might have some degree of consciousness. But here's where this connects to space and the cosmos. If consciousness is fundamental, it might be woven into the fabric of the universe at the deepest level. Some interpretations of quantum mechanics suggest that consciousness plays a role in collapsing quantum wave functions, turning possibilities into actualities. The universe might require conscious observers to become real. This leads to a mind-bending possibility. Maybe the universe itself is conscious. Not in the way you or I are conscious, but conscious nonetheless. The cosmos might be one vast mind, experiencing itself from countless perspectives. We would be like individual thoughts in a universal consciousness, or consider the anthropic principle. The universe has dozens of physical constants, values like the strength of gravity or the mass of an electron. If any of these constants were slightly different, stars couldn't form, chemistry would be impossible, and life could never exist. Why are the constants so perfectly tuned for life? One answer is the multiverse. Maybe there are countless universes with different constants, and we find ourselves in this one simply because it's the only one where we could exist. But another answer involves consciousness. Maybe the universe has the constants it does because conscious observers are necessary for the universe to exist. Without consciousness to observe it, the universe might be in a quantum superposition, not fully real. This sounds like mysticism, but it comes from taking quantum mechanics seriously. In quantum mechanics, particles exist in multiple states until observed. Some physicists think this applies to the entire universe. The cosmos might need consciousness to collapse its wave function, to make itself definite and real. There's also the simulation hypothesis. Maybe we're living in a computer simulation created by an advanced civilization. If that's true, consciousness might be the most important thing in the universe, because the whole universe exists to create conscious experiences. We might be like characters in a video game, and our consciousness is the point of the whole exercise. Or maybe we're about to create new forms of consciousness ourselves. Artificial intelligence is advancing rapidly. At some point, we might create machines that are truly conscious, that have genuine inner experiences. If we do, how will we know? How can you prove something is conscious? You can't look inside and see consciousness. You can only infer it from behavior. And if we create conscious machines, what does that mean for the universe? Does it mean consciousness is just information, processing, and nothing special? Or does it mean we're about to unleash new minds into the cosmos, expanding the realm of consciousness beyond biological life? The question of consciousness matters because it affects how we understand our place in the universe. Are we just complex machines, or is there something special about the subjective experience of being alive? Is consciousness rare and precious, or is it everywhere? Are we alone in having rich inner lives, or do aliens, animals, even plants experience the universe in their own ways? We don't know. After centuries of philosophy and decades of neuroscience, we still don't truly understand what makes us conscious. And until we do, there's a gaping hole in our understanding of reality itself. Question 3. Will the universe end? Let's talk about the end. Not your end or my end, but the end of everything. Will the universe end? And if so, how? This might seem like a depressing topic, but it's also one of the most important questions in cosmology. The fate of the universe depends on its fundamental properties. Properties we're still trying to measure and understand. For most of human history, people assumed the universe was eternal. But we now know it had a beginning. The Big Bang, 13.8 billion years ago. If it had a beginning, it's reasonable to ask if it will have an end. The first scenario is called the Big Freeze, or heat death. This is currently the leading prediction based on our observations. The universe will keep expanding forever, but the expansion is accelerating because of dark energy. Over trillions of years, galaxies will move so far apart that they can no longer see each other. Each galaxy will become an isolated island in an increasingly empty universe. Eventually, all the stars will burn out. The last stars will be red dwarfs, which can burn for trillions of years. But even they will eventually exhaust their fuel. The universe will be dark, lit only by the faint glow of dying white dwarfs and the occasional flash of matter falling into black holes. After that, even black holes will evaporate due to Hawking radiation. This takes an unimaginably long time. A black hole with the mass of the Sun would take 10 to the 67 years to evaporate. Supermassive black holes would take even longer, 10 to the 100 years. But given enough time, they'll all disappear. What's left is a cold, dark, empty universe filled with nothing but scattered particles moving slowly apart. The temperature everywhere will be just above absolute zero. Nothing happens anymore. No stars, no life, no change. This is heat death, the ultimate fate of the cosmos. Time continues, but nothing meaningful occurs for eternity. But there's another possibility called the Big Rip. If dark energy keeps getting stronger, it might eventually overcome not just gravity, but all the fundamental forces. First, galaxy clusters would be torn apart. Then galaxies themselves, then solar systems, then planets, then molecules, then atoms, then even atomic nuclei. Space would be expanding so fast that nothing could hold together. The universe would tear itself apart at the seams, and even space-time itself might shred. This would happen in about 50 billion years if the Big Rip is real. There's also the Big Crunch. If the universe doesn't have enough dark energy, gravity might eventually win. The expansion would slow, stop, and reverse. The universe would start contracting. Galaxies would collide. The cosmic microwave background radiation would get hotter and hotter as everything squeezed together. Eventually, everything would collapse back into a singularity, like the Big Bang in reverse. Some versions of this include a big bounce. After the crunch, the universe might explode outward again in a new Big Bang. This cycle could repeat forever. We'd be living in one cycle of an eternal series of expanding and contracting universes. Time would have no ultimate beginning or end. Then there's vacuum decay. This is perhaps the most unsettling possibility. Our universe might be in a false vacuum, a stable state that's not the lowest energy state possible. It's like a ball resting in a small dip on a hillside. It seems stable, but it's not at the bottom of the hill. If this is true, a quantum fluctuation could create a bubble of true vacuum somewhere in the universe. This bubble would expand at the speed of light, and everything it touched would be destroyed. All the particles we know would become unstable. The laws of physics themselves would change. A wall of destruction would sweep through the cosmos, and we'd have no warning. It could happen tomorrow or in trillions of years. The terrifying part is that we've calculated that our universe might actually be in a false vacuum based on the masses of particles we've measured. The Higgs boson mass suggests we're on the edge of stability. One leading physicist described our universe as precarious. We might be living on borrowed time without knowing it. But here's a wild thought. Maybe the universe won't end because it's cyclical in ways we don't understand yet. Maybe it constantly renews itself through baby universes budding off from black holes. Maybe information is never truly lost, and in some sense the universe is eternal, just constantly transforming. Some scientists have even proposed that the heat death isn't truly the end. In a universe that exists for an infinite amount of time, even incredibly unlikely events will eventually happen. Quantum fluctuations might spontaneously create pockets of order, maybe even new Big Bangs. Given infinite time, literally anything possible will occur, including the spontaneous formation of conscious observers like us, experiencing what appears to be a universe with a past. This leads to disturbing ideas like Boltzmann brains. If the universe lasts forever in a near-empty state, it's more likely for a conscious brain to spontaneously fluctuate into existence, complete with false memories of a life that never happened, than for an actual universe with a history to exist. Statistically, you should be a Boltzmann brain, a fleeting illusion in an empty cosmos, rather than a real person in a real universe. The fact that we're not Boltzmann brains, that the universe around us is real and consistent, tells us something important. Either the universe won't last forever, or there's something wrong with our understanding of probability, entropy, or consciousness. The ultimate fate of the universe is deeply connected to its deepest properties. Dark energy, dark matter, the nature of time, the validity of our physical theories, all of these determine how the story ends. Dark energy, dark matter, the nature of time, the validity of our physical theories, all of these determine how the story ends. Question 4. The Dark Universe. Let me tell you about one of the most embarrassing secrets in all of science. We have no idea what most of the universe is made of. I'm not exaggerating. When scientists add up all the atoms, all the stars, all the galaxies, all the gas, all the dust, everything we can see and detect, it only accounts for about 5% of the universe. 5%. Let that sink in for a moment. The rest? We call it dark matter and dark energy because, honestly, we're completely in the dark about what they actually are. It's like discovering that 95% of your own body is made of something you've never heard of and can't see. Dark matter makes up about 27% of the universe. We know it exists because we can see its effects. Galaxies spin too fast. They should be tearing themselves apart based on the gravity from the stars we can see. But they don't. Something invisible is holding them together. That something is dark matter. Scientists have proposed all sorts of ideas about what dark matter might be. Maybe it's made of particles that simply don't interact with light. Maybe it's black holes we can't see. Maybe it's something even stranger. Deep underground, in old mines and beneath mountains, scientists have built incredibly sensitive detectors, waiting to catch just one dark matter particle passing through. So far, after decades of searching, we've caught nothing. But dark matter isn't even the strangest part. Dark energy makes up 68% of the universe, and it's even more mysterious. The universe is expanding. The universe is expanding. That makes sense, right? After the Big Bang, everything should be moving apart. But here's what doesn't make sense. The expansion is speeding up. Think about that for a second. If you throw a ball in the air, gravity slows it down. The expansion of the universe should be slowing down too because of gravity. But it's not. Something is pushing the universe apart, fighting against gravity, and that force is getting stronger. Something is pushing the universe apart, fighting against gravity, and that force is getting stronger. When scientists discovered this in the late 1990s, they were so shocked that they double and triple checked their calculations. They thought they had made a mistake, but they hadn't. Some scientists think dark energy might be a property of space itself. Some scientists think dark energy might be a property of space itself. Maybe empty space isn't really empty. Maybe it has energy built into its very fabric. Others think our understanding of gravity might be completely wrong on cosmic scales. Both possibilities are mind-bending. Here's what makes this question so urgent. The fate of the universe depends on the answer. If dark energy keeps getting stronger, eventually it will tear apart galaxies, then solar systems, then planets, then atoms themselves. The universe would end in what scientists call the Big Rip. But if dark energy behaves differently, the universe might end in other ways, or might not end at all. We live in a universe where we understand only 5% of what exists. The rest is a complete mystery. And until we solve this mystery, we're essentially fumbling in the dark, trying to understand existence with our eyes closed. Question 5. Where is everybody? Now let's talk about one of the most haunting questions ever asked. It's called the Fermi paradox, and it goes like this. Where is everybody? Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. Many of those stars have planets. Some of those planets are in the habitable zone where liquid water can exist. The universe is nearly 14 billion years old. Our civilization has only been around for a blink of an eye in cosmic terms. Given all of that, there should be millions of advanced civilizations out there. Some of them should be billions of years older than us. With that much of a head start, they should have spread across the galaxy by now. We should see their signals, their spacecraft, their megastructures. The galaxy should be teeming with life. But we've looked, we've listened, and we've found nothing. Not a single signal, not a single sign. The universe appears to be completely, utterly silent. This silence is deafening, and it terrifies some scientists. There are many possible explanations, and none of them are comforting. One possibility is that life is incredibly rare. Maybe the chain of events that led to life on Earth required such an improbable series of lucky breaks that it almost never happens anywhere else. We might be alone, or at least incredibly isolated. Another possibility is that civilizations don't last long. Maybe every civilization eventually discovers technologies that destroy them. Nuclear weapons, artificial intelligence, climate change, engineered diseases. Maybe the window between developing radio technology and self-destruction is only a century or two. If that's true, it means we're in danger right now. There's an even darker possibility called the Great Filter. The idea is that there's some insurmountable challenge that prevents civilizations from spreading across the stars. The terrifying part is we don't know if we've already passed this filter or if it's still ahead of us. If it's ahead of us, it means our extinction might be inevitable, and we just don't know it yet. Or maybe advanced civilizations are out there, but they're deliberately avoiding us. This is called the zoo hypothesis. Maybe we're like a nature preserve, being observed but not contacted. Or maybe civilizations advanced enough to travel between stars have better things to do than talk to us. We might be as interesting to them as an anthill is to you. Here's another strange possibility. Maybe we're early. The universe is still young in some ways. Most stars that will ever exist haven't been born yet. Maybe we're among the first intelligent species to evolve. In 1 billion years, the galaxy might be crowded, but right now, we're pioneers. Some scientists have suggested that alien civilizations might be using forms of communication we haven't discovered yet. We're listening for radio signals, but maybe advanced civilizations use quantum communication or methods based on physics we don't understand. We could be surrounded by alien chatter and not even know it. The Fermi paradox matters because the answer tells us something profound about our own future. If the galaxy is empty because civilizations always destroy themselves, we need to know. If life is incredibly rare, that makes Earth and everything on it infinitely precious. If aliens are out there but hiding, we need to understand why. Every year we search, and every year we find nothing. The silence continues, and with each passing year, the question becomes more pressing. Where is everybody? And what does their absence tell us about our own chances of survival? Question 6. What came before the Big Bang? Here's a question that breaks physics. What happened before the Big Bang? We know the universe began roughly 13.8 billion years ago in an event we call the Big Bang. Everything, all of space, all of time, all of matter and energy, burst into existence in an unimaginably hot, dense state and has been expanding ever since. We have overwhelming evidence for this. We can see the afterglow of the Big Bang in the cosmic microwave background radiation. We can observe the universe expanding. The math works, the observations match the predictions. But here's where things get strange. If time itself began with the Big Bang, then the question what came before doesn't make sense. Before is a time word, and time didn't exist yet. It's like asking what's north of the North Pole. The question itself might be meaningless. But our brains don't accept that easily. It feels like there must have been something before. Even if time didn't exist, maybe something existed in some other way. Maybe there was a different kind of reality operating under different rules. Some scientists have proposed that our universe emerged from a previous universe that collapsed. Imagine the universe expanding and then contracting, collapsing down to a point and then bouncing back out in a new Big Bang. This cycle could repeat forever. We might be living in the latest version of an infinite series of universes, each one living and dying and being reborn. Others think our universe might have budded off from another universe like a bubble forming in foam. In this view, the Big Bang wasn't the beginning of everything, just the beginning of our particular bubble. There could be countless other universes out there, each with their own laws of physics, their own particles, their own constants. There's an even stranger idea called eternal inflation. In this model, inflation, the rapid expansion that happened right after the Big Bang, never really ends. It's always happening somewhere, constantly creating new pocket universes. Our universe is just one pocket that stopped inflating. But beyond our cosmic horizon, inflation continues forever, spawning infinite universes. Some physicists think that quantum mechanics might hold the answer. At the quantum level, particles can pop into existence out of nothing, borrowing energy from the vacuum for brief moments. Maybe the entire universe did something similar. Maybe it's a quantum fluctuation that just happened to keep going. There's also the possibility that the question is simply beyond our ability to answer. Our physics breaks down at the extreme conditions of the Big Bang. Time and space become meaningless. Cause and effect stop working the way they normally do. We're trying to apply concepts like before and after to a situation where those concepts might not apply. What makes this question so profound is that it touches on existence itself. Why is there something rather than nothing? That's perhaps the deepest question anyone can ask. The universe exists, we exist, but there's no obvious reason why any of this should be here at all. And here's something that will really bend your mind. Some interpretations of quantum mechanics suggest that the universe might have brought itself into existence. The act of the universe existing could have retroactively caused the Big Bang. Effect preceding cause. It sounds impossible, but at the quantum level, time doesn't always flow in the direction we expect. We may never know what came before the Big Bang, or if that question even makes sense. But the fact that we can ask it, that we can probe the very beginning of existence with mathematics and observation, that we can even glimpse the first moments after time began, that's extraordinary. We're standing at the edge of the knowable universe, peering into the void before existence, and we're not looking away. Question 7. What happens inside a black hole? Black holes might be the most extreme objects in the universe, and they're also the most mysterious. At their core lies a problem that has haunted physics for decades. What actually happens inside a black hole? First, let's understand what we do know. A black hole forms when a massive star collapses under its own gravity. The collapse is so complete that all the star's mass gets compressed into an infinitely small point called a singularity. Around this singularity is the event horizon, the point of no return. Once something crosses the event horizon, not even light can escape. That's why they're called black holes. We can observe black holes from the outside. We've seen stars orbiting invisible companions. We've detected gravitational waves from colliding black holes. We've even photographed the shadow of a black hole against glowing gas. But we have no idea what happens inside, because no information can ever come back out to tell us. This creates a fundamental crisis in physics. According to Einstein's general relativity, if you fall into a black hole, from your perspective, nothing special happens at the event horizon. You sail right through. Space and time get increasingly warped as you fall toward the singularity, and eventually you get stretched into spaghetti by tidal forces. But the journey across the horizon is smooth. But according to quantum mechanics, something very different should happen. Information, according to quantum theory, can never be truly destroyed. But if information falls into a black hole and can never escape, it's effectively destroyed. This contradiction is called the black hole information paradox, and it's one of the deepest problems in theoretical physics. Stephen Hawking made this problem worse, and then spent decades trying to solve it. He showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation means black holes slowly evaporate over time. Eventually, a black hole will completely evaporate and disappear. But the radiation coming out appears to be random, containing no information about what fell in. So the information is destroyed after all. Or is it? Some physicists think the information might be encoded in the Hawking radiation in ways we don't understand yet. Others think it might be stored on the event horizon itself, like a hologram. In this view, everything that falls into a black hole leaves an imprint on the surface, and that information eventually comes back out in the radiation. There's an even wilder idea called the fuzzball hypothesis. Maybe black holes don't have a well-defined interior at all. Maybe the event horizon isn't a smooth surface, but a chaotic, tangled mess of quantum strings. In this view, there's no singularity, no information paradox, just a complicated quantum object that we've been thinking about all wrong. Then there's the firewall paradox. Recent calculations suggest that crossing the event horizon might not be smooth at all. You might hit a wall of high-energy particles that instantly incinerates you. This contradicts Einstein's equations, which say the crossing should be smooth. Either quantum mechanics is wrong or general relativity is wrong, or we're missing something fundamental about how space-time works. Some scientists have even suggested that black holes might be portals to other universes. The singularity at the center might connect to a white hole in another region of space-time, creating a tunnel called a wormhole. Matter and information that fall into a black hole might emerge from a white hole somewhere else. It sounds like science fiction, but the math doesn't rule it out. Here's what makes this question so urgent. Black holes represent the ultimate collision between general relativity and quantum mechanics, the two most successful theories in physics. Both theories work perfectly in their own domains, but they contradict each other at the event horizon. This means at least one of them must be incomplete or wrong. Finding the answer will require a new theory, something that unifies gravity and quantum mechanics. Physicists call this the theory of everything, or quantum gravity. We've been searching for it for decades. String theory is one attempt. Loop quantum gravity is another. But we don't have the answer yet. Until we solve this, we won't truly understand what happens at the most extreme edges of reality. And black holes aren't rare curiosities. There's one at the center of almost every galaxy, including ours. Understanding them is understanding the universe itself. Conclusion. We started this journey by recognizing how much we've learned. We've mapped the cosmos, decoded the atom, unraveled DNA, photographed black holes. Human knowledge has exploded in just the last century. But standing here now, looking at these questions, we have to face a humbling truth. We don't know what most of the universe is made of. We don't know if we're alone. We don't know what came before the beginning or what happens at the end. We don't know what happens inside black holes, whether time travel is possible, what consciousness is, or what our ultimate fate will be. Every answer we find seems to reveal deeper mysteries beneath. It's like peeling an infinite onion, each layer revealing another underneath. And maybe that's the point. These questions aren't signs of failure. They're invitations. They're the frontier of human knowledge, the edge where wonder lives. Every generation before us faced impossible questions and found answers that changed everything. The questions we're facing now are harder, stranger, more fundamental than ever before. But that just means the answers, when we find them, will be even more revolutionary. Somewhere right now, a telescope is gathering light from the edge of the observable universe. A detector deep underground is waiting to catch dark matter. A mathematician is working through equations that might unify quantum mechanics and gravity. A philosopher is thinking carefully about the nature of consciousness. Grad students are staying up late, analyzing data, debugging code, running experiments. The answers are out there, hidden in the data, waiting in the math, encoded in the fabric of space-time itself. And humans, curious, stubborn, brilliant humans, are going to find them. These are the biggest unanswered questions in space, but they won't be unanswered forever. The universe is waiting, and we're just getting started.